Perfect. I think MCPs are really something very great, and I hope at the end of this, I don't know, 45 minutes, an hour, we will come to this conclusion that it's much, much bigger than we think it is right now. And I would like to build this up with an example. And here's my question. What is the capital of France? When I'm asking this a language model, in this case, I'm asking this Mistral on my local computer, and the answer comes back, the capital of France is Paris. Okay, that is of course correct, but how does this work? Like, how did it come to this conclusion, right? Somewhere, this neural network, this language model needs to store that information, that Paris is the capital of France, and I don't know, Vienna is the capital of Austria. So where is that actually happening, right? If you think about computers, in computers, it's pretty simple. We have a central processing unit, right? The CPU. It could also be a different kind of processing unit, like a GPU. And then we have a RAM, which is a random access memory. It's a super fast memory where we can access randomly any point of this. And then usually we have some other larger kind of storage, like a hard disk storage, right? And if you want to retrieve some information, like what is the capital of France, what we actually need to know for that is we need to know the address where that information is stored. So either it's stored in the memory, then there's a memory address that says like, well, here is that the answer to this question. Or if it's stored on the hard disk, then it could be in files, then we have a file allocation table, or it could be in a database. In any case, we need to somehow find where did we store this information, right? So we treat it by knowing where it is, and then the where is, of course, done with indexing and so on and so on, right? Now, if we look at a neural network, and this is like a schematic image of this. Remember, you have the input layers in the beginning, and then you have some hidden layers. In this case, they're red. And then you have output layers, which is green. Where is it stored here? There is no obvious place where this information is actually stored. And it's a very important piece to build up to and to understand. We don't see it in that way. We see it with computers because the storage system for a neural network is entirely different than for computers. It's not based on knowing the address, but it is based on knowing pieces of information. So you know a little bit of it, and then it fills out the blanks, basically, right? So we call this an associative memory system. Now here I switch to this image, basically. So you have a part of it, some pixels, let's say maybe these here, and then based on this, it finds the rest of the information and brings you and retrieves the system back for you, right? How does it work? Well, we can look at it basically in a Hopfield network kind of way. So we have these connections between these neurons, these artificial neurons. And this connection in a recurrent neural network is actually in both directions. So there's one forward and then there's one back again, right? And red in the images that I'm going to use means it's excited, and blue means it's not excited. So what does excited, not excited means? Ultimately, an artificial neural network is a very rudimentary copy of our brain. And in our brain, we have these cells, which are neurons, obviously. And these neurons can have a property, and the property is they can change their voltage, and they do this by a very complicated mechanism, which is mostly triggered by chemical processes. But what it really means is there is a cell that can change its state, and it can be basically on or off. So it can be 1 or 0. Okay. And this is, by the way, not only neural tissue, but also muscles work the same way. Now, red for us means it's a 1, and then blue means it's a 0 in this case, right? And then we have a connection, and this connection, we say here is 0.7 or minus 0.4. What that means is that the higher the number is, the more weight that this 0 or this 1 carries on to the next one, right? Think of whatever is here in the middle as in your brain as the synaptic cleft. So you have the from edge one, the axon going to the synaptic cleft and then releasing some, neurotransmitters. And on the other side, you have receivers basically to take this signal and then translate it back to another signal. Right? Now, to understand how information is actually stored in such a thing, we can borrow a concept from thermodynamics. So the idea here is the following. We can calculate different energy levels for states, right? So in the right side, you see basically states. There are 3 neurons. 2 are excited, 1 is not excited, and you see the connections in there. So it's +3 from C to B, and then -2 from B to A. And I have only one error here because it's the same weight going back in both directions, right? That makes it easier for our calculations. Now, you see here on the left side the energy formula. Basically, what you need to do, or what you're doing, is this. You take you calculate for each of those connections, right? You're calculating this term here, which is the weight. So in this case, it's the -2. And then the state of these two. So it's one would be 1 and the other one would be 0 in this case, right? And then you sum up all of those connection formulas, and then you get a total energy. Now, the system basically tries to minimize the energy in a state. So meaning that if there is a lower energy, then it's a preferred state of it. And if it's a higher energy, then it's not a preferred state of it, right? It's an unstable state of it, right? And if we take this as an example here, if we have here these kinds of formulas, so if both of these neurons are excited or both of these neurons are not excited but are negatively connected to each other, then it is in a good state, and if not, then it's a bad state, basically, right? And it's very simple, because if you put it into the formula, you will get either a higher energy state or a lower energy state. Right? So ultimately, this is how we are storing information in this neural network. And if we calculate the energy levels here, you will see that we take, so here all 3 are excited, so they're red, so it's a 1 here everywhere. And then we take these weights, multiply it, so 3 times 1, right? So this is this one here, and A to B, sorry, this one here, and then A to C is this one here, and so on, right? Now, we can calculate it for both of them, and then we get our energy state of -2 and +4. So the right one is a not stable thing. That's not a state that is storing some kind of information. And then the left one, it's a stable one because it's a very low energy level. So this is a level where we are storing something, right? You can think of it, if you plot it in this manifold that you've seen already. So whatever is very low there, that's the state that we want to be. So that's where we are storing some information. And then the red is where we're starting. So we have a piece of information there, right? And it follows way down to the lowest energy state, which in this case is here. And that is basically the answer to your question, right? Like down there, it says basically Paris to the question, what is the capital of France? Right? This is how we're storing information. It's an entirely different way of storing information. It mimics much more how humans actually store this information. Because think of it this way. If you're hearing a part of a song in the radio, right? And you know the song and you like the song, it's very easy for you to recall the song based on a very small piece of that song. If you would store this in a computer system, it's very, very hard problem to solve, right? Because now, if you have just a piece of a song, you don't know where it is in your storage system, so you have to go through a whole storage, right? The whole song for every song, and try to find this information. It takes basically forever, right? So it's a brute force method of doing this, where in this way, associative, you see a part of it, and you can immediately get to the answer, which is the song, right? And by the way, this is how we are. I mean, there are different ways of storing information, basically, but this is how we are also storing our memories and these kind of things. And all of us who have been sometimes even in an exam situation where you just have a blackout, you can't remember, and then the professor or whoever gives you some hints. It's like, think about this or think about that, and then suddenly it makes click and you remember everything. Right? That's exactly what's happening here, is because it's putting you in a certain position from which it's easy to get to this memory state where you have the answer stored. Of course, if you have actually stored it and if you have learned it. So if you think about this, then learning actually means updating weights, right? And that is also how it is for humans. I mean, of course, we don't have weights in that sense in humans, but we have these connections, and connections can be stronger or less strong. And we have a rule which is called the Hebbian rule, which is if it fires, what fires together wires together, right? So basically, we have a rule how these systems work. We don't know exactly how it works on a chemical process. Definitely not the way we're learning with artificial neural networks, which is backpropagation. But somehow we are building these connections there. And somehow we are also being able to do this with neural networks. Neural networks, as I said, we have a prediction might deviate from the intended. Oh, sorry, there's some sound here. Yeah. So I just put it. The way to fast these models to refine our model. Sorry. Okay. So basically, we are here in this case now going forward propagation, then predicting, and then adjusting the weights in the backward propagation. And with these weights, we are building a memory state where we can store this information. Right? That's our purpose of all these things. Now it gets actually a little bit more complicated because what they call a so it gets a little bit more complicated because in a large language model we have several layers, right? So we have these multi-layer perceptrons, and then we have these attention layers, as you know, and these things are repeating sometimes very often. So it's a huge network that we need to train to learn something, right? And just to be sure, that's the only way a language model is storing information, which means that if you take a cutoff date, right, and it has been trained till, I don't know, 2024, everything that happens after that is not stored or not encoded in these weights. And if you would like to have it stored there, it's a lot of work to do that. Why? Because you have to retrain the network for that. Now, a retraining of these neural networks can be very expensive and very difficult. Why? Because we have these scaling laws. And what the scaling laws, and we have talked about this in others in other webinars, they're very important because they basically dictated what happened in the last couple of years when it comes to language models. So it's all based on a research paper that Dario Amodei and a few others at the time at OpenAI wrote, which is if you scale up the compute, the data set size, and the parameters in some relationship to each other, then you can predict that the error that a language model is doing is going to decline, right? And now this is logarithmic scale. So whatever looks here linear is not linear, unfortunately, which means to really make these systems better, we have to put so much more compute data set size and parameters, right? In fact, when we go from GPT-3, for example, to GPT-4, right, the size of the scaling that we had to do to get almost like approximately double as good was 100-fold. So we scaled it up 100 times to get double as good only in these things, right? So that's of course a big problem, right? And if you look at the cost associated with it, it's very clear that the cost is increasing. Again, this is on the left side a logarithmic here, and this is only till 2024. But you can assume that we are above $1 billion now already with these training things. So it's very expensive. So any time that you want to train a neural network of new knowledge that comes out, right, you need to go through this process, which is a very difficult process. Now imagine you want to use this to answer questions about your procedures in a business. That would mean that you would always need to retrain the system to actually answer those questions, so that this knowledge, this new knowledge that you generated, or new procedures that you generated, are encoded somehow in this knowledge, right? It's a very expensive, very difficult process, takes time, and so on. Right? And it's not only expensive, but also we need lots of data to do this. And as Ilya Sutskever once said, I think in a very interesting conversation. He said, well, there's only one internet, right? So these things have been trained basically on the whole internet, but there is only one. And there is not a second internet, which means that at some point we're going to run out of data. And there is some analysis here, and the analysis says that, probably somewhere at 2027 till 2030 something, we'll run out of data, meaning, and I'm here talking really about these large language models, right? Meaning that there will not be enough, not more data to actually scale these things up, right? Actually, I think that data is not the biggest problem. Before we get to these data constraints, and we also talked about this, there are other constraints that we are getting to, right? So one is power. So these things need, of course, lots of energy for cooling and other things, and that is, problematic because energy is not easy transportable. So even though you would probably generate enough energy in the world, it doesn't mean that you're generating enough energy around that location where the server farm is that is doing these calculations. Right? So there is some things that need to be taken account there, and I think we are at the third nuclear power plants that Microsoft has ordered. Like I think it is 3, at least that was the public news. So just imagine there is a company who is going to own 3, as of now, 3 nuclear power plants because their power consumption is so big that they actually need to build these things for themselves. So I live in Germany. We don't have a single nuclear power plant, and in Austria is the same. We actually built one in Austria, but it never was connected to the grid. So you see that energy is a big problem here. And then another problem after data then comes, of course, is chip production, right? So as you know, it's not so easy to produce these chips, and I'm sure you have heard a lot about chip wars and other things like where are those produced, and it's a geopolitical risk that are involved there and so on. But anyway, it's not easy scalable to tomorrow we're going to produce more of those things. Now, this problem that we have, right, with this energy consumption and all those things to actually train this model gets even worse. Why does it get worse? It gets worse because the things that we call reasoning models, right, and it's not only reasoning models, but mainly reasoning models, are achieved by giving a model more time at inference. So we are basically saying, find a solution to the problem. Like, how do we, what's the best way to get from here to the airport, right? And then it iterates through several ideas to find this out, right? So it could, I could take a train, we could take a cab, we could, whatever, do certain ways to get there. And that is happening at inference time. So when you ask the question, and that is why you're waiting that long for something, right? So yesterday, I think it was yesterday or the day before, OpenAI released a new part of their API, which is asynchronous now, because sometimes this latest generation of model is O3 Pro, is thinking so long that the connection to the server is being disrupted. So you have to need to have a asynchronous connection there. So it can time, and at the time these things are doing something. They're doing lots of calculations, right? So actually, if you think about this, and I don't understand me wrong, I like reasoning models a lot. But essentially, these reasoning models are not reasoning in a mental projection. They're reasoning in the token space, which means that if I would ask, let's say Vincent, what is the best way to get to the airport? And then Vincent would just try out all the ways. So he would actually order a cab and go to the airport and then come back and then do it with a train and then come back and then walk there. That's exactly what a language model is doing when it is reasoning. It's because it's translating everything to the token space, which means that in reality it is doing those things that it is thinking about. It's not a mental model where we think, oh, if we do this and this, so we're actually doing this. So which means lots of tokens are generated. And if you watch the Google announcement, they showed a 1,000-fold in the usage of tokens, but they don't have a 1,000-fold usage. What they actually have is maybe a 100-fold usage or a 50-fold usage, but the rest is actually more token consumption because of this let's verify step by step, which is test time compute. So you are computing at inference time. Right? So it gets even worse. And all the prediction says that ultimately we'll probably use as much of energy in the inference than we do in training. So there is a lot of issues there by adding new knowledge to the system through training, which is basically adjusting weights. Now, there is luckily another way. And this other way stems from something that I've also shown you, and I can only repeat. I think this is the one of the biggest moments that generations will look back at, which is this in-context learning. So after training all these things, these large language models sometimes have emerging capabilities, so capabilities that we haven't planned for, but they emerged. And these emerging capabilities are also something like this, that it can now learn by instructions. So we call this, in this paper, it was called in-context learning. And in this example, researchers gave the language model following example. So they said, here's the input, 2014-0601. And the output is exclamation mark 06, exclamation mark 01, exclamation mark 2014, exclamation. Right? So why exclamation mark? Because it's a date format that doesn't exist. So we know that the language model has not been trained on this, right? So there is no training data set where it has been trained on this specific kind of a format. Now, after they end basically here, right? And the green thing is what the model completed. So the model actually answered the question correctly, but it learned what it needs to do through the instruction and not through the learning process, not through adjusting weights, but through instructions, right? And that's huge. And of course, you should, you can, of course, read this. It's very interesting, these emergent abilities. And if you look at the examples in this paper, it's fascinating because the system picks up abilities that not only nobody has trained for, but nobody even could have expected, like answering questions in Persian, right? That's one of those things that they highlight in this paper. And now we can also apply this to something different, which is this chain of thought, which is basically the start of this reasoning models, where you tell in the prompt, in an example, how to solve an issue, right? What is the steps that you need to take to solve this specific issue, right? And that prompts the language model then to repeat a cognitive step-by-step process, like decomposing a bigger problem into smaller steps and then doing step by step, which ultimately then gives you a better result, right? Now, the important part of this is social learning. So basically, you can now teach AI something, which is not necessarily done through this associative memory that we have been discussed before, but through instruction. You basically are telling this to do this, right? And that's a very, very big change. And then really something that it was always clear that AI cannot do, but now it can do this. Now, how are we using this in real life? We are using this in real life with something which is called RAG. And this RAG has created dozens of products, dozens of companies even. And the idea behind this is very simple. So it's actually from Meta Research, and RAG stands for Retrieval Augmented Generation. And the idea is this: if I have a large corpus, right, of new information, like policies in my company or whatever, and I would like to answer a question, what I can do is I can first go and search the chunks, the pieces of information where the answer to the question is encoded in. And then I can take these pieces and add them to the question, right? So basically, if we take it to the financial industry, if you ask this question, what is the maturity date of a loan in a credit agreement, then usually this maturity date is not actually written there. It doesn't say it's that date. It often says the maturity date shall be 7 years after the closing date if such date is a business day, right? Now, you need to go and take different chunks of information, like what is the closing date? You need that piece of information. Then you need the business day conventions and the holiday calendar to actually calculate the maturity date, right? So you take these pieces of information, give it all to the language model, and then you're saying, hey, Mir, please answer this question. And in the context, you gave it all the information it needs to actually answer this question. Now it just needs to reason along these chunks of information that you gave it, and it does that. Of course, this thing can get like super complicated because selecting these chunks is very difficult, right? So the chunks need to be somewhat in context, and then sometimes you want to do a dense vector search, which is a similarity of meaning, right? A semantic search of it, but you also sometimes want to do a lexical search, like the way the word is written. So you need to support those things, and so on and so on. And then how do you build these chunks? It's not an easy problem to solve. But after you have received this, then it continues, because then you have to do, or should do maybe a re-ranking, like what is the best result, and so on and so on. And so there's a lot of things that get into this rack that are, difficult to build, and you have to build all these things for you, right? So you are building actually a sparse vector store and a dense vector store, and so on, right? So these are the things that you need to build to have such a thing. Now, of course, there are other ways of doing it. There's something which is called CAG, and then the knowledge graph, augmented generation, and so on. But the things that they have all common is you need to build tool sets, right, that retrieve certain things for you that gives some more context to the language model so that you can actually answer this question. And you hear repeatedly the word context, and that will give you a hint where we are going now, right? So remember agents, right? So agents are basically a system where you have a sensory input, so it can, read a page, or get some information into it, right? And then it has a reasoning engine, so some kind of engine where it makes decisions based on this input, and then an actuation, so doing something out of this, right? And if you give it then a purpose, a goal, then you have an agent, right? And I think there's a lot of discussion about what is agentic, what is not agentic, what's an agent, what's not agent. I think that is not so. On a technology level, it's not that important. I think where it gets to be very important, and this is where I urge everybody to think about this, it's only an agent if it has agency, right? So if it can decide something itself. If it doesn't decide anything itself, but it is like pre-coded things, then it doesn't have agency, because somebody gave it basically this rule set, right? And as soon as you give it some agency, you have, of course, a bag of problems, because now how do you make sure that it's aligned, and so on and so on. But besides the bag of problems, you have like fantastic results too, right? And how do we achieve these results? Basically, we achieve it through flexibility now, because before we had a fixed plan, right? And now an engineer, whoever was writing a piece of software, for example, had to take all cases into consideration and have a path in the code, in the program, that answers this specific case, right? And if not, then it is something which engineers call undocumented feature, and then everybody else would call it a bug, right? Because then suddenly something stops and something unexpected happened, right? So here in an example, I think this is funny, right? So the idea here is basically, if you give it really a hard-coded step-by-step, any change in the environment can lead to a big problem, basically, right? And with agents, you are actually solving exactly this problem. What are the capabilities that they need to have is, or what they can do is they can, of course, do repetitive tasks, but also multi-step tasks, and then, collaboration. And the most important thing is human-like reasoning. And I know, of course, that Apple has released a paper a couple of days ago where they are saying that this reasoning is tricky, actually, right? Because it is not always really reasoning. That's the first thing, right? And then the other thing is that if the problem gets very hard, then it actually takes less time to solve it. So almost like if I ask a very difficult question, it doesn't think, it just blurs out something. But if I ask an easier question, then it quote unquote thinks, right? And so they're saying it's actually not a thinking per se. And I think there's a semantic issue here. But I agree with their findings. It's very well documented. But at the same time, I would argue that humans are exactly that way. If I would ask a question and force at gunpoint to answer, then if you really have no idea what it is, then you would just blur out something, right? And that's exactly what these models are doing. So they're maybe too humanistic rather than not human-like, right? Now, of course, you need some kind of cognitive architecture, how you're building this plan or how you are iterating through this plan, right? And there are, of course, several systems for this. And I think we talked about this, and one very, very widespread and important one is what we call REACT. And REACT is about reason and act. So basically, you're thinking about how to get to the airport. And so you're saying, okay, so what's the next step, right? The next step is you need to go down out of the apartment or the house, right? So that's the first step. So you do that. And then, so what do I do now? And so with each step, you're trying to get closer to that solution, right? What is important, though, of course, is that it's not guaranteed that that aggressive way, right, of trying to find a solution will always lead to the best solution, right? Just think of sometimes it's better to drive a longer way, but do it on a highway rather than going through a city with a shorter rate, right? So this React thing, in essence, if you don't give it the right weights, it would actually always find the shortest thing, but not necessarily the fastest one, right? So you need to work on those things, but generally it is a pretty good framework. It's very, very it's very adaptive, right, to the environment. So anything that changes, it can immediately plan because it doesn't have a long-term plan and so on. Now, of course, it has also disadvantages, and the biggest disadvantage is, of course, that it takes too much time, right? Because just imagine every step you're reasoning again, and then doing a step, and then reasoning, and then doing a step, and now think you're doing 40 steps. Each of those you're reasoning a couple of seconds. It takes forever to get to an answer. Another way of doing it is you can think of a whole plan up front, right? You can say, oh, okay, I do the whole plan up front, and then I execute this, right? Which has the advantage that it's faster, but now it's less flexible, right? So if something unexpected happens along the way, it has a problem, right? And there are, of course, other, cognitive architectures like critique and revise, where you have a language models rethink and critique itself, basically, to get a better point. And these things work surprisingly well, right? And we are thinking oftentimes, why does it work well, right? If you ask a language model to critique its own results, like isn't a language model the thing that produced these results? Like, wouldn't it come to the exact same result again if you ask the question again or let it critique? No, and no, because of two reasons. So one, of course, it is a probabilistic system, but even if we take away the probabilistic part of it, no, because it has a different starting point, because now this first answer and then the self-critique is part of the context window, right? So it is nudging the vector's internal representations, right? And you can think about it also in a different way, which is that and it's also a very good model for the human brain is small world networks, right? So what a small world network is a network where you have regions, these small worlds, where they are very, very well connected with each other. And then this region is connected with another region not as well, right? So it's not like everybody's connected with everybody, but there's a region that is connected very well with each other. And then there's a little connection to some other state, right? And so, and these we call this small network world is probably how we're thinking, right? So we are thinking about a problem, and then now you're in a small world, and maybe the solution is not in that small world, but somewhere else. So you need to find a way to get from here to the other place, right? But that is difficult. It is difficult for humans as well. It is difficult for AI, right? In humans, basically, a way to do this is, when a professor asks you think about this, right? Then you get to another state. And with AI, getting this is critiquing itself, where you basically add now more information to the context window and make it more likely that it leaves basically one small world and goes to the other small world, right? So that's why these things are working surprisingly well. And then you have some others, and I don't want to talk about multi-agents right now, but I will talk about this later. Now, if we go back to our React way, right? The way we can look at this React is this. We have a start where we get a problem, right? Let's find a way to the airport. And then we are analyzing this task and determining, okay, what's the next step? How do I get there? We determine the next step. And then we go, okay, do we need more information to actually answer? Yes or no? If no, then we can go and formulate the answer already. So we're done. And if yes, then we have a set of tools, right? In this React. Now these tools are, in this case, it's like a search and a calculate, and I just wrote here retrieve data, right? These are tools that connect you to this outside world. And if you remember, we called this sensory input, right? And it would be, if you would need to answer the question how to get to the airport, you probably need a public transportation map. You need a way to look up how much it costs to order a cab, and how long it takes, and so on, right? So these are then these tools. Then you invoke these tools, you get some result out of it, and then you analyze, okay, now do I now have everything that I need to answer this question? Right? And if you do, then you formulate the answer, and you're done. There is a chance that you're not, then you go back again. It's basically this treat here, go to another either same tool or another tool and ask a question there, and you iterate through these things and go through this. Now remember, when we talked about RAG, right? That's exactly, so these two things are very similar to each other, because all these functions that you're doing here, searching in a sparse vector, searching in a dense vectors, and so on, right? You can see as a tool that is doing that. So if you would take this into a tool or this into a tool, then you're mimicking exactly this image here, right? So these two are basically similar by transforming this searches here into these tools here, right? Now, why is that important? It's important because what MCP has done, and I think we can't, overstate the importance of this, is what MCP has done is it has standardized how these tools are accessed by language models. So meaning that now you don't need anymore to write all these things yourself. There are MCPs out there who can do that work for you. So you don't code it yourself anymore. You don't need to write a retrieval through a Postgres database, a retrieval in the internet, and so on and so on. You can wire in tools that do these things for you. Now, on paper, right, it doesn't seem as much, right? But it's almost like if you take the cord away from a telephone, it doesn't seem as much either, right? So instead of having the telephone then in some room with the cord connected to the wall, it's not connected to the wall. Great. But what it actually meant for humanity is like probably nobody could comprehend at the point that it happened, right? Years later, we understood, oh, it changed everything. It changed how we interact with technology, how we organize our life. Everything changed because of this mobile first revolution. And I think the same is going to happen here, because we just don't know what it means to us if we simplify the process of the software creation. The last time we did this is when we went from assembler, basically, right? Went from assembler, which is zeros and ones, more or less, to a programming language where you could give instructions that are closer to language and easier to learn, right? And that was huge. Now this is potentially even larger than that, because now you don't need to do anything anymore. You can just wire those things in, and AI will figure out a way to use them. So basically, I think of an MCP is doing to capabilities what RAG did to knowledge, right? You remember how great RAG is, because RAG now allowed that we don't need to retrain, and we can, inject knowledge there, right? So the function that we added to it is we don't need to retrain, but we can inject knowledge to it in a different way. And now we don't need to program, but we can inject functionality to it, capabilities to it. And that's very important because we cannot even comprehend what capabilities will be necessary, right? We think of these capabilities a lot of things that we are able to do, and we forget all the things that it could do. Sorry, I'm just turning on this. All the things that it could help us to forget things. It could help us to things that are not close to don't come immediately into mind, right? But forgetting is one of the most important things for intelligence. So I think that we just cannot. Nobody probably can think of all the capabilities that this thing can add to this, right? And what it will do, and here are some examples, right? So for example, Postgres, right? So basically, you now have a tool to store things into the database. What does it mean? It means you don't need to think about queries anymore, like selects and so on. It will construct them automatically. And then you don't need to think of how to store it and to build these things. It will do these things automatically for you. Vincent, I think you have a question?
Yeah, there's a question in the chat. Are our ontology models as necessary or valuable with MCPs?
Yes, absolutely they are. I think they are. Why? Because so just to for everybody, well, an ontology is a knowledge organization system. How do you organize knowledge, right? That's what an ontology is telling you or defining for you. And it is the most flexible way of organizing knowledge, which means that it can have different kinds of connections to each other. So why is that important? It is important because a knowledge graph through an ontology is a concrete storage of information, right? So it's a concrete state, like this is a loan, this is a bond, or whatever. It's a very concrete. Whereas a dense vector, which is the foundation of these language models, it is a very, very, very good average of something. But even the best average of something is still an average of something, right? And not a concrete state. Now, these concrete states happen actually, and this is, I think, the important part of it, very often don't happen as per nature defined. What do I mean with this? When I say this is a large company or this is a small company, this is now a concrete state that, I know a company like Google is a large company, but where is the line? Where do we put the line that it's large or it's small, right? It isn't something that's dictated by nature. It's something that I choose for myself or somebody chooses for myself, right? So ontologies are important to, first of all, decide how you want to organize your knowledge, but then also to set the limits, because these things where or the classes where you put something in is very, very different based on your use case, based on your view on the world, based on what you think is important and so on, right? So it's always a very important piece of connecting these two worlds with each other. And it has this beauty that it also gives you somewhat of an explainability that without knowledge graphs is very difficult to achieve. So yes, I think knowledge graphs are actually, and you see it actually in point 2, knowledge graph server here, are a way of having as it says there, semantic memory layer on top of a vector search, for example, right? But even further, right, you think of AWS. So there is an AWS MCP server. So now you don't need to write these complicated infrastructure as code statements to spin up a server in a region, but you can just do it in natural language, and this AWS MCP server will translate it to the correct commands that it needs to actually do this work. Right? Same is true for, I don't know, Trello boards and other things. And there are thousands, literally thousands of these things that are coming every day, almost new to the system. And each of them is adding a capability to it, right? It's not just adding information, it's just really a capability to it. So now it suddenly can store information in Postgres. Right? Almost, you can think of almost, it's, if you have seen Matrix, the movie, when they, say, I need to learn this or that, then they just put something into the keyboard, and then suddenly the knowledge or the capability of something is wired into the brain of the person. And that's exactly what these MCPs are doing in a standardized way. And we cannot overstate that fact that it's standardized. I think it's so important that it's standardized. Now, what it will do to programming, and I think that's the important part of it, right? What it will do to programming is huge. I think we cannot even estimate this, right? Basically, if you think of code right now, it is a system where we are determining, or I mean engineers are determining the output, are determining the flow, are determining all the possible functions that a code can do, right? So you're writing everything from zero, basically. Now, with AI, this changes slowly, right? You can now add, as a first step, some LLM calls to it. So rather than a deterministic output, like here's an error message, you could route it through an LLM and make a witty error message out of this, for example, right? So you don't know now exactly what the output is going to be, but the room of possibilities is very small, right? Because it can only change the last output, basically. And then you can also build pipelines, so take more of these calls behind each other. And then you can make decisions in your routings based on AI, right? So I decide that based on AI that you are in an opera watching a beautiful opera. So when you look at your watch, it's not going to turn on the light because it's dark out, right? Whatever, right? These kind of things, or mute your phone automatically and these things, right? So these are the routers. And then state machines, where you now even allow cyclical workflow. So you go back to the point one again, to square one again, right? And that introduces a whole bag of difficulties. But besides difficulties, it also introduces lots of opportunities that we can do with this, right? And then, of course, a fully automated way of code, right? Which is this code written by agentic tools. Now, why is it important here? This is why it's important. So Google released Alpha Evolve, which trains itself to develop algorithms for coding, right? And what it has done is, and I think this is such a big moment. It's like this this aha moment. What it has done is it has solved problems, or a specific problem that humanity couldn't solve for over 50 years. And when I say humanity, I don't mean me, but I mean the really intelligent, mathematicians couldn't solve how we are going to do this for 50 years. And then this AI thing solves it in record time. I don't know the time, but it's like hours maybe, right? So you can see that, and this is, why is that possible? Because it is altering itself, right? It is basically altering, like it's going through an evolutionary process in itself, but that process at a speed that, is not every 25 years, but every 25 nanoseconds maybe, right? So it's huge speed. Then you wire in some feedback. Oh, I need to change this, and then suddenly you get to an answer, right? So I think it's really, really huge, and it's huge because of two reasons. So one, it is huge because the speed that things are going to happen is unprecedented, and I think we should even think about this a little bit deeper. Harari the other day said, the question remains if we are going to slow down AI, or AI is going to rush us until we, and he's used extinction. I hope that's wrong, but that's what he said, right? So you see that the speed really picks up, and you can see it in many, many, many different areas. And it's huge because of, that. But it's also huge because we can solve problems now that were unconceivable to be solved in it, right? Like problems like cancer and other things in a much, much faster way. Of course, there's also, all difficulties and problems there. And how do you observe this? How do you make sure that the results are right? How do you make guardrail this? How do you, and there's 100,000 of problems. But there is also these huge advantages that it has, right? And I think that MCP is, in reality, the first step of it. Because what we have done with MCP is we have developed now universal tools that all AI agents can use, right? It's almost like Homo faber, right? The human now, we are at the stage with the AI where we can develop tools, and these tools are not only usable by us, but they're usable by anybody. Just imagine what it has done to economy, to the world, and so on, right? And now take this speed that it took us, 10,000 years. How long will it take AI? Now, but the real explosion of humanity was not tools only, right? Because if you think of what is, a difference between a chimpanzee and myself, if we put both of us into an island, the probability that the chimpanzee survives is much higher, right? Especially if there is no microwave, because I would like die out of hunger in the next day already, right? They're just much more adept to they're stronger, faster, and so on. Right? But how is it then, if that's the case, right? Then how is it then that humanity is ruling the world and chimpanzees are in zoos, more or less, right? Like, why is that? Like, how is that happening, right? And Harari tried to answer this question in Homo Deus. And the idea is that humans can coordinate in large groups, whereas chimpanzees cannot. Chimpanzees can coordinate in like 15, 20, but after 20, it gets to be problematic, right? Whereas humans can coordinate in 100,000. 100,000 people can go to a stadium and watch a game, right? So they coordinated to do this. And of course, we coordinate to much more important things as well. And it is this coordination that probably led to this explosion of humanity. And these tools, MCPs, are only the first little tiny step of it. Because the next step of it is how agents are going to talk to agents to coordinate themselves. So now agents talk to tools, but then agents can maybe soon talk to agents itself. That thing is already there as a protocol. It's called HOA from Google as an example. Of course, Google is not the only company is doing that, but it's a very well thought thing. And now if you take this also in the equation, then you can already almost see, how fast it is going to be that, these agents really take true agency of what they're doing in code and other things, and coordinate themselves to build massive things at a speed that is not comprehensible right now to us. So I think MCPs are the biggest first great step of it, but also only just the beginning of a huge thing that is coming to us. Any questions?
Don't be shy. I think probably everybody is more or less at the hour to proceed to the meetings. Let's.
Okay, then if you have any questions, you can always email. The last thing that I want to say is really, I know that MCPs are always looked at. Oh, now it can talk to an API in a better way, right? But I think it's just so much more than this. It's not just that. It is really a reusable tool across things, and that's huge for almost any area that I can think of. So think of really MCPs as the beginning of something very, very big.
All right, thank you very much. I think please come to us, email us, get in touch if you want to understand how this works in practice, how it looks in our platform. We purposefully do not make these webinars promotional and talk about ourselves. So if you are interested in a demo or a discussion with Vahe or one of our experts, please get in touch. There's actually one last question, Vahe. When will there be an MCP server which can book my flight tickets or perhaps organize my family photos, similar to the AI in the movie Her?
I don't know that movie though. What was the movie called again?
Her.
I don't know this one. But I would think that there is already an MCP, isn't there? I can look this up. I think there could be already an MCP for this. But if not, then you can be very, very sure. I think with 100% certainty, you can assume that Expedia and Co is already working on an Expedia MCP. Like there's no chance that it's not happening. And I think you could with Tabili and other things that do an internet search, you could probably already do the internet part of it. And then with this browser automation, you could theoretically, I think you could do it already. It's probably in a too complicated way of doing it, but either there is one already or there will very soon be one already. So it's probably a matter of days, even not even weeks, I would assume. And the photos, I honestly, I never take photos on my phones. I have no idea. But I thought that they're already doing this, aren't they? Aren't they like sorting all these things? Like Apple, didn't they release like a couple of days ago something around that? Sorry, I can look up the other thing, the booking flights, but with photos, somebody else needs to help. No idea.
All right. Yeah, thank you once again for being part of this conversation. Until next time, take care and have a great rest of the day. Thank you, Vahe, for your time.
Thank you very much. Thank you.
All right. Thanks a lot.